So, well, first of all, thank you for the organizers for allowing me to present my work. My topic here of interest is interacting supernova, so something a bit different from what we've done so far. Now, what is the interest behind this is the fact that we know that there is a non-significant fraction of the observed supernovae which are actually not well fitting into the usual boxes of type 2p, type 2l, and so on and so forth. And instead, we have some supernovae which are labeled here with this greenish dashed line, which have signatures of the fact that the supernova itself is interacting with some circumstellar material. And they make up roughly 15% of the observed supernova from the Zwicky-Chenziv facility with a magnitude limited sample. So that's a bit of a caveat. The thing that we aim for is to see whether or not binary evolution can help explain the development of such interacting supernova. And the reason for this is the following, with this little sort of cartoon thing. So basically, before or shortly before core collapse, one thing that happens is that perhaps the binary system loses a lot of mass, either through mass transfer or eruptions, you name it. This material moves away from the binary, thus forming a CSM. And then the idea is that when the supernova explodes, you have basically two effects. First of all, it's the ionizing photons coming from the supernova itself. They excite the material. And it basically means that the CSM will have exhibit neural line emission. Counterwise, also we have, in the case of the explosion itself, you're going to release a lot of matter, which will just impact on the pre-existing CSM. And that has other features that will affect instead the light curve rather than the spectra. So the idea is, well, let's look at systems which undergo Rorschach overflow close to core collapse. We'll see how close. Yeah. So this is a snapshot from the Milky Way binary grid that we have in Bonn. It's developed by Harim, and I don't know where she is. But yeah, shout out to her because this is basically her work. Here I've labeled in gray systems which have at least reached core helium depletion, and then in white systems that have merged or undergone unstable mass transfer, and I'll discuss that a bit later on. So the question is, can we find primaries which are undergoing Rorschach overflow prior to core collapse? And the reason for studying primaries is that we can then connect them with the initial mass function and initial distribution. So that can give us an easier outlook onto the probability of said systems. I haven't done that yet. I have some just rough results, but yeah, we'll just go on with that. Now, looking here at the log PQ diagram, so each box is basically a binary simulation with an initial mass ratio here on the x-axis and initial orbital period on the y-axis. And they're divided between case A, B, C, and then non-interacting systems. So here we see that there are basically two clumps of material of systems which undergo another phase of mass transfer shortly before core collapse. One of them is, of course, the KC systems. That's a bit by definition. And then we have two lots of case B systems, which undergo another phase of mass transfer shortly before core collapse. It's either the very white binaries, in which case they retain a little bit of hydrogen and expand again after core helium depletion, so enough to undergo mass transfer. And here instead, on the bottom panel, these are very tight binaries post case B mass transfer. And the primary here is a helium star, which is low mass enough to expand and fill its Rorschach loop once again. I will ignore for now case A systems because here in this mass grid, they just result in white dwarfs. So basically we can split this group into two sort of classes of systems, either wide red supergiant binaries, of which we have two papers that have been both accepted, and low mass helium stars plus main sequence binaries. Here on the x-axis, on the bottom here, I've illustrated some of the physics that really would affect these results. My confidence into how much they affect this goes into basically what the emoji says. And yeah, basically we took some of the models from the binary grid and we rerun them as close as possible to core collapse. So let's start off with the red supergiants. Here I'm showing you the mass transfer rate as a function of time prior to core collapse. on the left panel. On the right panel, it's the envelope mass as a function of time. The first thing that I want to point out is that we have that KC models can be stable even with relatively low mass ratio of about a half. That is because we use basically the fact of whether or not the primary also overflows its other Lagrangian to distinguish whether or not mass transfer is stable or not, with its caveats that we have already discussed. So basically, models with high mass ratios, they tend to to undergo stable mass transfer, and more importantly, they do so up until basically core collapse, which means that for the case of interacting supernova, you will have a dense CSM. Probably, you will have a dense CSM nearby the system at core collapse. We also have the systems which have instead undergone unstable mass transfer, and those are the little diamonds. And we see that in some instances, the onset of unstable mass transfer happens extremely late in the evolution, even less than just 1,000 years prior to core collapse. So then the idea is that in those cases, you're just going to eject a lot of material all of a sudden, but then the supernova is going to happen soon after. So then what happens is that you have basically a helium core plus the main sequence star that starting spiraling, and they're engulfed in this very massive CSM. And then by the time that the explosion happens, what happens is the ejecta will immediately interact with, will immediately ram into this very heavy CSM of basically about 6, 7-ish solar masses. And that will definitely cause interaction features, especially in the light curve. Okay. Also, as it was mentioned yesterday, there are many caveats in the case of red supergiants. Namely, we have pulsations which are not taken into account here. We have the fact that these systems should be eccentric because the binary basically was extremely wide at ZAMS. So there is no reason to believe that the orbit circularized. And also these should have extended atmospheres, which would probably change the parameter space for mass transfer. Now, instead focusing on low mass helium stars, which now have a main sequence binary, main sequence companion following case B mass transfer, here I'm now showing again the mass transfer rate as a function of time prior to core collapse. And on the bottom panel, the mass of the helium-rich envelope. Well, actually, how much helium there is in the remaining envelope. Now, the first important thing that I want to highlight is that much like the red supergiants, they tend to fill their Roche loops until very close to core collapse. So again, the CSM will be pretty dense, close by the supernova, well, the progenitor star when the supernova happens. So in that case, you should have narrow line emissions, which should be then detectable. If we also look at the fact whether or not this mass transfer is stable, and it's always stable because it's case B that already has flipped the mass ratio. So this is always happening from, it's always mass transfer from a 2, 3, 4 solar mass helium star onto like a 6, 7 solar mass helium star. And yeah, basically this would also suggest that they will have interaction features, and most of all, in some instances, the final helium content in the envelope is so small that perhaps we are also not just switching from perhaps type 1b progenitors, but also going down as maybe 1c or even ultrastripped. So I'll try now to put everything together in the log PQ diagram once again. So let's start then by filling the systems which do not undergo a second phase of mass transfer. So we have that the widest systems are just boring red supergiants, and so type 2p supernovae. And then for the case B systems, those that have retain a little bit of hydrogen, those are type 2b supernova, and then the remainder just type 1b. We can also fill in then the wide red supergiant binaries that undergo mass transfer. In that case, we can allegedly say that the ones that undergo unstable mass transfer are likely to exhibit superluminous features just because of the dense CSM surrounding it. And likewise, those that have undergone stable mass transfer should likely exhibit just narrow lines. If we instead focus on the helium stars transferring mass, they would likely be type 1b and supernova, or even transition to 1c here. But now, one important thing that I haven't mentioned so far is that the stability of case B mass transfer actually would affect the results that we would expect. That is because right now, the models that are not colored have undergone a merger because it was either inverse mass transfer or a cap in the mass transfer rate. We can use more physically motivated criteria. So for example, the luminosity criterion from Pablo, and that would basically destroy the majority of this parameter space. So what I'm trying to say is that the assumptions on the stability of mass transfer would affect the amount of some specific supernovae from happening. And so you could, in theory, use this as another tool to basically say how stable mass transfer should have been based on the number of these systems. There is a big issue that I haven't come across in that last slide, is that, well, from 1D models, we cannot predict the structure of the CSM. And that is extremely important. And that's also why I've always said may become type 2Ns, may become 1BNs, and so on, because it really depends on the structure of the CSM, which we cannot predict from CSM from just 1D models. So crucially, if people could do this with SPH simulations and so on to give us the structure of the CSM, that would be great. And then we just have to give it to the supernova people and yeah, give us the results. Thank you.
Cool. Thanks for Andrea. I have one, which is maybe this comes from knowing too much about engineering stars, but one of the big uncertainties in especially, the ones doing sort of case B or later mass transfer is kind of when they overfill their Roche lobe. And a lot of this, because these stars are convective, is sensitive to your treatment of the convective envelope. And you mentioned whether or not you turn on MLT++ makes a big difference. Have you also explored, even just kind of in classical mixing length theory, changing alpha, your mixing length alpha, not your common envelope alpha, can if you change alpha by a factor of 2, you can grow or shrink your radius by a factor of, at least 50% or more. Have you explored kind of, the difference between, say, an alpha of 1 versus alpha of 3 and how that shifts this around? Does this only matter kind of above periods of 398 and the, type 2-ish adjacent ones, or is it important?
So this would basically just provoke a shift in the parameter space, because at the end, you're just changing the point in which the red supergiant becomes wide enough to undergo another phase of mass transfer. I wouldn't know if just the KC band becomes larger or smaller, because it really depends on the maximum radius that you achieve before helium ignition. And the star shrinks and then it expands again. So I'm not sure how different values of the mixing length theory parameter would change the contrast between these two radii. But one point that's made in Luc Dessart's paper, which is based on my models, is that perhaps the mixing length parameter that we use is a bit, produces too extended red supergiants. They should be...
What value did you use?
I use 1.5.
Yeah, that's too big. Luke has been saying that since 2013. But yeah, I mean, I ask in part because I'm curious how much uncertainty that adds in this space. If it's subdominant compared to all of the other uncertainties, then maybe you don't have to worry about it. But it does get your red supergiants sort of puffier, cooler effective temperatures, and also not necessarily consistent with the early UV and supernovae.
Yeah, but we haven't done a systematic study in this. We just said, oh, let's just run a few models and see how that would change. But we didn't do this extremely systematic.
Makes sense.
Yeah, that's actually a good thing to look into. Thanks.
Yeah.
To be just for red supergiants or in general?
Well, so red, yellow, basically anything that has a convective outer layer or even subsurface convection, your radius becomes very sensitive to how efficiently you get out the flux.
Yeah.
And so when you crank alpha up, when you crank up the mixing length, you can get it out more efficiently. Your surface becomes, your surface becomes smaller. It would be kind of like having a lower opacity. If you know metallicity but don't know mixing length theory, it can sort of mimic-ish the effects of lower metallicities, for example. Yeah.
How much then?
You can change, so if you change the mixing length from 1.5 to 4, you change the radius of the star from 400 to, or sorry, from 900 to 400.
Oh.
But then
It
if
is
you
a
do
big-
it too much, you switch into yellow supergiants.
Yellow
which we do
supergiants,
not
it maybe matters more.
Yeah.
And then blue supergiants, it matters less because you have very little subsurface convection. Other questions? I have plenty, so I can keep going. But I guess how does this? So we heard earlier that there's kind of rapid population synthesis that's also making predictions for sort of what the ratios of these are. How do you see? Yeah, how does this work fit into that space?
So
Yeah.
Tentatively, so the binary grid that we have is not just the 12.6 solar masses. We span from 5 to 100. So in that case, I did some preliminary work, and it seems that under some assumptions, we do get similar results of the ratio between type 2 to type 1 and so on. The thing is that we do observe this, that's a bit the point here, that there are also these interacting ones, which from what I know in population synthesis and so on, you cannot really capture this phenomenon. It's pretty intricate. It's pretty just from detailed binary evolutions that you can maybe have this. Maybe we can develop some prescriptions here that then can be applied in binary population synthesis. And that's a bit what I'm trying to achieve here.